Welcome to Astronomy, Chapter 3. In this video, we're going to be looking at the third chapter of our text called Light and Telescopes. In this chapter, we're going to look at a brief view of what's going on to describe a little bit about the nature of light and a little bit about this amazing invention we have called the telescope that has completely opened our view on the universe. Now, this chapter starts off with a little bit of instruction about how light can be broken down into its pieces through a device called a prism. And a lot of this work was actually started right where we left off in chapter 2 by Isaac Newton. Newton was very important in describing how this light can be broken apart into its specific wavelengths. And then later in the next chapter, we'll look at how we can actually study this wavelengths of light and what they can tell us about an object, which is very exciting. We'll look at that in the next chapter. Now, in here they talk a little bit about the nature of light, how light moves quickly, how it behaves as a wave, and explains a little bit about the basic fundamentals of the motion of light. The one that you need to know that is, of course, light travels very, 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 very fast. Light is the fastest thing we know of, but it does have a speed limit. And that speed limit is about 186,000 miles per second. And so when you think about that, that's a staggeringly fast speed. That means to get from the Earth to the Moon only takes maybe, it's less than a second and a half to get light from the Earth to the Moon, which is very, very far away on human scales. But it is fast, although it is a set limit. Now, one of the things that they go into next that we would be remiss if we didn't talk about, that has to be in every physical science and certainly every astronomy text, is what's on page 74, something we call the electromagnetic spectrum. The electromagnetic spectrum is one of the things that we talk about a lot, but isn't necessarily very well understood. And what it really is it's just a range for the different types of light. Light comes in many different types. And those different types of light have different purposes. Of course, the light that we are most often interested in is here in visible light. Visible light is the light that the human eye is sensitive towards. The light that we can see, giving us the colors of the rainbow and the effect caused by the sun. Largely is where we see visible light. But all of them have their different uses, and there simply is a range of the wavelength, which is, we see this compression of the waves from large waves to very small waves, be from very low energy waves to very high energy waves. Gamma, and really there's even things above gamma, cosmic rays and things of that sort that are considered even higher energy, but nonetheless, this spectrum, or this range of different types of light, is a crucial part of understanding what we're going to be looking at in this chapter. So make sure you get a brush up on this if you don't remember how the electromagnetic spectrum works. You do need to be familiar with those different types. Now, moving on to the section on telescopes here. They give you a picture of a replica of Isaac Newton's telescope, which was a small reflecting telescope that he built to help understand the nature of light. And that adaptation of using a mirror is actually shown well on the next page on 76. They explain some of the basics of what we call optics. Optics is a study, a subdiscipline of physics, where we look at the nature of how these light rays are being moved around and how they are brought to a focus and what that does and how that accomplishes a task. And of course, the task here is to use a large mirror or lens, and we'll get to lenses in a minute, but to use something to collect light. And that's why telescopes are often called, a slang term is to call them a light bucket. They're simply a bucket to catch as many particles of light. And of course, a particle of light is called a photon. We're trying to catch as many photons as possible. And because when we catch a whole bunch of photons, we can brighten them and magnify them to give us a better image. And that's ultimately what we are doing. And the most important rule you need to know about all telescopes that they go through explaining here with this concept of resolution is they explain that the one and most important rule is bigger is better. In telescopes, there is no substitute for a bigger mirror or lens. The bigger you can build that mirror or lens, the better. Now, a standard sized telescope that someone may have would be maybe a couple, 3 inches in diameter. That would be a reasonable thing that an individual might own. A decent portable telescope, like some ones we'll use in this course, will be 8 inches in diameter. And when we travel out to the observatory, the main telescope we use will be 24 inches in diameter, 2 feet across. Now, the largest telescopes in the world right now are about 10 meters across. Think about that for a second. 10 meters, that's like 32, 33 feet across. Huge, huge mirrors. And it won't be long before those are going to be considered small based off some of the new telescopes that are being designed and planned that will be 30 meters and upwards even to 40 meters across. That's roughly the size of half a football field in terms of a mirror. Very, very large structures. And the bigger the mirror, the better the image we can see. That is an absolute fundamental rule. Now, one of the exciting areas, a new technological development is talked about on page 80 in this text, with how do we analyze this information and how do we store it. Virtually all light that is collected now is stored digitally. And we do this because that allows us to do so much more processing. It's much faster. It's much easier. We have made tremendous leaps and bounds improvements in digital detectors that we see in, a digital camera or even in the cameras that we see now in smartphones have become very, very good and have become very, very affordable. And of course, those are called CCDs, or charge coupled devices. But nonetheless, the newer technology has been making great strides to help in astronomy. The next part here when they talk about telescopes is they talk a little bit about refracting telescopes, and they talk about a lens bending light. Now, this process is actually what the human eyeball does. Your eye has a lens in it that curves light to achieve the same thing as a curved mirror. That is, to gather light and bring it to a focus. Now, the largest refracting, that is lens-based telescope in the world, is shown here on page 83 at the Yerkes Observatory just outside of Chicago. And you can see, if you look in this picture, there is a person here and a really big long tube. Refracting telescopes can be very difficult to manage because they have to be physically very, very long as they get bigger around. And mirrored telescopes don't have that limit. Mirrored telescopes are compressed in size, which means they're much easier to manage. And it is for that reason, and that reason mostly, that all of the major telescopes that are built now, all of the big telescopes, are reflecting type, not refracting type. This type of telescope was made before the turn of the 20th century, and it will almost certainly remain as the largest refracting telescope ever built. You just simply can't make them much bigger than the Yerkes Observatory. Moving on towards the end of this, one of the big problems that all telescopes have, and they show you this very nicely on page 88, actually comes from a children's song. And we all know this song, Twinkle, Twinkle, Little Star, How I Wonder What You Are. Well, why the twinkling, right? We've all gone outside and seen stars that appear to twinkle. Why do they do that? Well, stars twinkle because of the atmosphere. And this atmosphere causes slight distortion in the light. Now, it makes for a pretty effect, but for an astronomer, twinkle is the enemy. Because that twinkling causes a distortion, and when we zoom in really, really, really close, we see more and more and more of that distortion. So we have to figure out ways to get around that distortion caused by the atmosphere. The way that we do that is you simply either put a telescope in space above the atmosphere, or you use an ingenious invention called adaptive optics. Adaptive optics is a very exciting area of astronomy where we measure the distortion of the atmosphere, which is constantly changing, by the way, at any given location, and then we subtract out that effect in real time using a computer. Fabulously cool piece of technology that allows us to make really big telescopes on the Earth rival our great observatories in space. The Hubble Space Telescope, the James Webb Space Telescope, Kepler, Chandra, and others, now that we have a variety of telescopes in space. Hubble will probably always be the most famous of those, being the first truly successful space-based observatory. And of course, it produced such amazing information because it didn't have to look through the atmosphere. So, the atmosphere is really the enemy for astronomers. Now, there is one other area of astronomy where telescopes can be used. That's kind of an exciting new area, and that is to use observatories, use new technology that will allow us to look at energy, that is, types of radiation, in different parts of the spectrum, not looking at visible light. So we have now observatories that look in the ultraviolet, that look in the X-ray, that look in the gamma, that look in the infrared, that can see in a wide range of the electromagnetic spectrum, not just looking in the visible part. This is a very exciting part of astronomy that's growing rapidly right now. So those are the main features that we see in Chapter 3 on light and telescopes. Make sure that you're keeping up with your reading, reading through the text on this, and that you are using the PowerPoint attached to this section, and then you'll be ready to start Chapter 3. Homework. Good luck.